Warm welcome, everyone. Thank you for being here. Get yourself ready with a notebook, a pencil, or pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a multiple choice problem, quick one. When I say quick, I mean you need to be quick. So go ahead and pause the video. Give yourself about 2.5 minutes. Work this out for yourself first. And then when you're ready, come back and pause the video, whatever you gotta do. And see how we did it here. Or you can try to follow along. Okay, let's get started. So we want to find the volume of a region. That's funny. It actually should be volume of a solid, because the region doesn't have volume. Formed by... Oh, I get what they're saying. Yeah, it's kind of weird wording here. If I didn't write these problems, I would have written them with slightly different English. I would say find the volume of the solid generated by revolving the region formed by, maybe I'm just being a semantic jerk. So let's represent the region. You should be very comfortable with doing that extremely quickly. We're going to rotate this around the y-axis. So the goal is to find the volume. Here is our grid. We have x equals 3. We'll just put that like right here or something. And we have x squared. It's going to look something like that. It's going to grow very quickly, right, guys? And then we have the boundary at x equals 3. So we might as well draw that. And we're rotating this around the y-axis. So let's three-dimensionalize this a little bit. There's our z-axis that kind of goes into the page, and it also comes out. What we're doing is we're taking these two curves, and we're wrapping them around like that, so that we have an outer ring and an inner ring. Okay. We're taking slices dy because we're rotating around the y-axis, which is a vertical line. Anytime you go around a vertical line, you're going to want to do dy. You could also do the shell method dx, but nobody really talks about the shell method. It's not necessary. So how far am I going to be taking these slices? Like the bottom slice, right, it's going to look like this. And it's not really going to have an inner circle because the inner curve is just at the pole. But then as we go up, we see these sort of circles which are the same size, you'll notice, because the outer boundary is the exact same size the whole time. It's this length of 3 that's going to be the radius. So let's get an idea of these cross-sectional slices. Remember that finding areas, rather volumes, in calculus, it all comes down to being able to represent the area of the cross-section slices. So here in this case, we have a center point at the rotational axis, that's the y-axis. And then we have this little radius, which represents the closer curve. That comes from y equals x squared. But since we're differentiating, or rather integrating with respect to y, we need to change this to say x equals plus or minus square root of y. And this particular graph is the positive square root. The negative square root would be going down here. Would be going back here to the left, to the negative side of x. And so we're going to put square root of y. Oops, it's a confusing color to use here. Square root of y. And then we have the longer radius, which represents the distance from the axis to the furthest boundary. And that's just a constant of 3. So the area of each one of these slices, or one of these washers, is going to constitute everything inside of the big circle, but outside of the little circle. It's basically going to be pi big R squared minus pi little r squared, or just pi parentheses big R squared minus little r squared. And we need an actual, equation for that. So this is going to be 3 squared minus square root of y squared. So this is going to be 9 minus y. Pretty easy, actually. And the volume is simply going to be the integral from what to what? Yeah, from where to where? but we're starting at the bottom at 0, and we're all the way at the top at 9 because this is when x equals 3 meets the graph of y equals x squared. So we're just going to add up all of these slices, and that's fairly easy to do. This is going to be pi times 9y minus y squared over 2 from 0 to 9. Of course, plugging in 0 doesn't do anything, but when we plug in 9, we get 81 minus 81 over 2. I see so many students struggle with this kind of thing, but it's very basic. If we take a number and we subtract half of it, we're left with the other half. So that's just 81 pi over 2. Don't worry about getting the same denominator and then you subtract 162 minus 81 and you get 81. Just think about it logically. We're taking a whole number and we're subtracting half of the number. How much is left? Like, take a cookie and then break it in half. Take half away. How much is left? It's half a cookie. So 81 over 2 pi is our answer. Okay, so this is the washer method. Remember that whenever you're rotating a region around a vertical line like the y-axis, you're going to be doing dy integration. And you're going to end up with some washers here because we're not rotating it around one of the boundaries. You'll notice that one boundary, let me erase some of these disks. One boundary is that close curve that is this parabola y equals x squared. That's one boundary, but the rotational line is the y-axis, so we're not rotating it around one of the boundaries. The other boundary is all the way out here. If we were rotating it around the line x equals 3, then for sure we would have just had disks because there would be no gap in between the boundary and the rotating line. But since there is a gap in between this rotating line and the two boundaries, we have the close one and the long one, then there's going to be washers involved. Okay? All right, that's enough blab out of me. See you guys next time in the void.